Today we want to talk about taking up space with length, area, and volume. So I want to start with just a point. Even though we usually represent points with these gigantic spots that have some kind of area, they even have volume. This is literally volume of a gel sitting on top of a piece of plastic, but we're thinking of it as a representation of a single point. It's taking up no space. It is zero-dimensional. So we want to see this point and we think this is taking up no space. That's the whole idea with a point. That point is not taking up any space. What we're going to do is start adding dimension. We're going to start adding dimension to our point. So let's give ourselves one dimension, left, right. That's one dimension, left and right. Left is just -1 times right. So it still only counts as one. So we're going to take this point and we're just going to drag it along our new dimension. So I'm going to take my point and I'm going to pull it along our one dimension. And this is going to give us a length. When things take up this kind of space in this way, we call that a length. Well, we want to think about taking that point that we started with and dragging it along our first dimension into an interval that has a length. We drag our starting point. Oh, and this is one-dimensional. We're going to drag our point along our first dimension. And our point will get dragged into an interval that we measure with length. We drag our point along our first dimension into an interval with a length. Now we're just going to repeat the process. Now that I've got this length, I'm going to turn this into area by picking another dimension, adding another dimension that we're allowed to move into. I'm going to take the same interval and I'm going to add a second dimension. This dimension is going to be up and down. So I'm going to take my, let's see, I'm going to take this interval with its length, and I'm going to drag it through a second dimension. I start off, our first dimension is going to be left, right. Our second dimension is going to be up and down. So I'm kind of jammed at the top of the paper, so I'm going to pull it down. So here's our original point, got dragged through the first dimension over there. And here's our first line segment, got dragged through the second dimension into this rectangle. Now we have a two-dimensional object. Now we have a two-dimensional object, a rectangle with an area. So we drag our interval along a second dimension into a rectangle with area. This is not new. This is what we've done before. I'm going to say the distance that we drag it into our second dimension is going to be called the width. So I'll call that the width. And we know that our area is just going to be the product of the length and the width. Area is equal to length times width. This is not just what we use for the area of a rectangle. This is how we even think about area. There's some length, there's some width, and we multiply those two. This is why we have square units, square feet, square meters, square centimeters. Because it's centimeters times centimeters, and when we multiply things, we square them. That's why it makes sense that the area is the length times the width. And so now we have area. We get area by dragging length through a second dimension. We're going to build volume in the exact same way. We're going to take area and drag it through a third dimension. So here is our rectangle. We're going to build a volume by doing the same thing. I'm going to grab this area and just pull it into a third direction, a third dimension. This dimension is going to be forward and backward. And I'm going to have to approximate my forward and backward because I'm drawing on a two-dimensional thing, mostly a two-dimensional thing. I mean, there is some thickness here, but I can't draw in that space above the paper. So I'm going to do the usual thing. We're going to pretend, we're going to trick our brains into seeing something in 3 dimensions. So I'm just going to take this and drag it into a third dimension. So I'm going to do that at an angle here. So here's our original point that got dragged into a length and then got pulled down into an area and now has been stretched backwards or pulled forwards into a volume. Here's a length. Here's a width. And we just added a third dimension by taking this and pulling it forward. It looks like I started in the back and I pulled it forward. So I pulled it forward. That's the one I'll label. Since that's the one that's coming out of the page, we'll call it height. And now I've got a 3-dimensional thing. And we did the same thing what we did before. We dragged our rectangle along our third dimension into a solid. And we're going to say that the solid has volume. Furthermore, the volume of our solid is just the product of the length, the width, and the height. We'll also notice that in the volume equals length times width times height, that length times width came from the area. So to get this volume, we just took the cross-section area and multiplied by the height, because this is just how stuff works. It was what we did when we calculated area. It's what we did when we, we started with 0. So I guess we started with length. But once we had that, any other dimensions, we just multiplied them. And so we took this cross-sectional area and multiplied by the height. So volume is length times width times height. It's the cross-sectional area multiplied by the height. And this is what we think of with volume. Started with a point taking up no space. We drag it along one dimension to get a length. We take that length and drag it through a second dimension to get an area. Take that area and drag it through a third dimension to create a volume. And this is just like what we mean by length, area, and volume. Any questions? Nothing new, maybe a slightly different way of thinking about it. That will serve us later on. Now we could keep going with this. It becomes difficult to picture because I've used up the 3 dimensions that we normally think of: left, right, up, down, forward, and backward. Anything that I move, anywhere I move my hand now, that's just going to be a combination of those. If I go up, I go this sideways thing. That's a combination of left and right and forward and back. This is just a combination of left and right, up and down. This is just a combination of all 3. For those of you who are at home, I'm moving my hand back and forth in different directions that aren't just flat, left to right, forward and backward, or up and down. Everything is just going to be a combination of those 3. I'm not doing anything new. I can't imagine drawing another line that's not using those 3 that I've used already. But we do the same thing. If we could imagine a 4th dimension, right? If we existed more often in a four spatial dimensions, if we existed in like a 4 with a 4 spatial dimensions that we could normally perceive, then I would just take my rectangular solid and drag it through a 4th dimension. Take those 8 points that we have and pull them along. And then that would make a 4-dimensional thing. And we would calculate the 4-dimensional volume of that thing, length times width times height times depth, let's call it. And those first 3, length, width, height, that would just be the volume that we had in 3 dimensions multiplied by the height that we dragged it through. Then this can keep going. 5 dimensions. Take that 4 dimension, drag it through another 5th dimension. Any questions? The most common thing to do, by the way, is to take a cube. I don't know if this is the most common, but this is certainly popular now that Marvel has made movies about with these kinds of things. Just take those 8 points and just like expand them out. So this point's going to go up to here, here, and here, here. And then just kind of drop these down lower. It's hard for me to picture like where they're going to go, but this point is getting stretched out through some dimension that we haven't used yet. Then this point gets stretched out through some dimension that we haven't used yet. And then this point gets stretched out through some dimension we haven't used yet, and so on. And it always looks terrible when I draw it, but this is why. I've taken this four-dimensional thing and or like in this picture, I've taken a three-dimensional thing and I've made a two-dimensional representation of it, right? I've squashed out one dimension. Here, I've squashed out two dimensions. That would be like trying to draw a picture of, let's say, that chair, but squash two dimensions out of it. Not just draw a flat picture of it, but draw a one-dimensional picture of it. And so let's see, the chair looks like, well, that. Because we're missing too much information. We're missing dimensions of information. But we just keep doing the same thing. We take that cross-sectional rectangular solid and multiply it by whatever distance we pull it through our fourth dimension. A lot of times we like the way we do things. The reason that we do things is we want to see what happens to a shape over time. And so we'll make the fourth one time. But in this exercise, we're thinking of a fourth spatial dimension. So our hypervolume, our four-dimensional volume, is in meters to the fourth. Because it's meters times meters times meters times meters. And the next one that I would draw, we would just grab our 16 vertices and extend them through another dimension. And it would just start looking like a cube suspended in another cube. But stuff is getting really weird because our normal spatial perception is in three dimensions. I've talked to some fifth dimensional beings and they tried to explain it to me and they were just kind of making fun of me because I couldn't picture it. And I go, ah, stupid human. And there are 3 dimensions worth of perception. Any questions? So why is this relevant to our interests? So what does this have to do with calculus? Remember, calculus is about infinity. Calculus is about the difference between the continuous and the discrete. Calculus is about looking at something that is continuous, continuously changing, and modeling it with some discrete change. We're looking at something that is continuously changing and modeling it with a discrete change. We lower the resolution on the continuum that we see and develop tools to understand things that way. Even though on this screen, this question mark looks like a curve, right? When I draw it with the pen, it's this curve, but the screen cannot display that curve. It's just giving you a bunch of points, but it's making them small enough that we can't see that the little individual corners in all the pieces. So our mind says, that's curvy. And then the computer screen is like, oh, they think it's curvy. But that's because we can't see close enough. So it's creating a model of this continuous line that I drew with a discrete collection of points that are small enough that we can't see them. So this is what we do in calculus. This raises the question that we had at the beginning. How close is close enough? And the answer is, eventually you'll just know. You just have to know. We're building an instinct. So what's that? How does that show up in this kind of thought? Area is equal to length times width. Remember that one of the questions that we deal with calculus is finding area under a curve and above an interval. We want to calculate an area under a curve and above an interval. For whatever reason. I haven't justified this at all. For those of you who have secret mathematical knowledge, yes, we're headed towards integration. We're headed towards the thinking behind integration. And I haven't justified why we would want to do this. The reason that we want to do this is that area is calculated with multiplication. Anytime we can use multiplication to answer a question, that's a time when we're going to want to use this integration business that we're leading to. We're going to want to find the area under a curve, not because the area under a curve is so important, is that the area does not just have to be length times width. The area could represent a distance. The area could represent a distance, which is equal to rate times time. Or it could represent an amount of work, which is force times distance. Or it could represent anything that we use multiplication for. The applications of this kind of thinking and this integration are exactly the applications of multiplication. Here's what changes, and here's why we need to have calculus. So I want the area under a curve and above an interval. So let's draw a picture of that. To keep things simple, we like to represent our curves with functions. This is because it's the simplest for us to work with. It doesn't work on everything, but it works on enough that it's super useful. I want the area under this curve, and let's say above an interval. Here's what we know about area. Area is length times width. Not just for rectangles, but for everything. This is the concept of area. Length times width. Area is equal to length times width. Not just for rectangles, this is how we think of area. It's just a length multiplied by a width. That's just how we define area. The problem that we have in this area under the curve is that the length is continuously variable. That's the issue that we have. The length is continuously variable. So I want to say, here's my length. But when I go to grab the value for length, I'm like, oh, well, shit, it's like continuously changing. My width is like, oh, yeah, I'm just an interval. Don't look at me. It's the length. That dude is the problem. I don't know if the width would hang out, would let the length hang out that much, but. So the problem here is the length is continuously variable. So this is the job for calculus. Calculus is how we deal with shit that is continuously variable. What happens when things are continuously changing? I want to do length times width, but one of my factors is continuously variable. That's a problem. So let's think about what happens if we want to do multiplication, but things are just different. So we know that if I have multiplication, I can use multiplication five plus 5 plus 5. I can summarize with multiplication because all my terms are the same. So my terms are the same. That means we get to use multiplication. That's the whole point of multiplication. We got tired of doing 5 plus 5 is 10, 5 is 15. It's like, oh, what if we just simplified this and remember that if we have 3 5s, that's 15. And then we made a times table. We, like I was there. But if the terms are different, then we just add them up. We're stuck with multiplication. If I've got 4 plus 5 plus 6, here the terms are different. So we're stuck with addition. When the terms are different, we're stuck with addition. Here's what we're going to do with our continuously variable problem. I want to calculate area, it's length times width. That only works when the length is constant. The length isn't constant. So what we're going to do is we're going to make the length constant. That takes care of the continuous part. And we'll make it constant on small little pieces. That takes care of the variable part because then we can just use addition. So we're going to look at length times width, and I'm going to break this length into pieces. I made this 2.5. I could have made it 3. I knew I wanted to draw 3 rectangles. I could have made it 3. And I made it 2.5. Why? I don't know. I wasn't paying attention. But we're going to imagine it doesn't have to be evenly split anyway, so I don't know what I'm worried about. If we lower the resolution off of continuous down to discrete, now I can use multiplication and addition. I can just add up some rectangles. That's how we deal with the continuously parts. Variable parts, we just use addition. Continuously parts, we stop things from changing. Now we have a place to put the plus signs. We're going to break the region into rectangles. That will allow us to use multiplication and addition. Now we have a place to put the plus signs. The function is continuously changing. There is no next value of the function. If we pick a real number, there is no next real number. If we pick an integer, there is a next integer. If I pick an integer n, the next integer is n plus 1. And if I want to add them up, I just put a plus sign in between them. We can do that with a discrete set. A discrete set is a numbered set, and I can put a plus sign in between all of my elements, all my terms. In a continuum, we don't have that option. In a continuum, there is no next real number. So there's nowhere to put the plus signs. We're modeling this continuous change with some discrete change. So I'm going to use this value for a little while, then I'll switch and use this value for a little while, then I'll switch and use this value for a little while. And then how do we improve this approximation? Make more rectangles. How many rectangles should we use? Infinitely many rectangles, because this is calculus class. And that's what we do. We take our approximation, figure out how to improve it, and then just do that forever. Then shit gets kind of weird because I'm doing length times width, but my widths keep getting smaller. My widths start going towards 0. So I've got some length multiplied by a 0 width. And isn't that going to be 0? Clearly not, because there is definitely some area here. Any questions? You can't just look at where things are headed. You have to look at how they are getting there. What a great metaphor for going to school. Students tend to not listen to Yoda. Always to the future, this one's never thinking about where they are, what they're doing. You know what I mean? You can't be here just because in several years you're going to have a job. You have to get what you can out of this experience that you're going through now, that you chose to go through now. That make sense? You're only ever going to get out of school what you put into school. The amount of effort that I can put into your learning is necessarily less than the amount that you're going to put into it. That make sense? How's everybody okay? Sometimes it's not going to be like fun and you're not going to see the value in it. But that's got to be on you. You've got to find a way to put the value in it. Instead of thinking about what the school is doing for you. Think about what the school is doing for your education. Think about what you could be using the school for your education. What could you get out of it? Does that make sense? This is important. Because the schooling that you're doing now is optional. And if you don't want to do it, then don't. If you're not getting anything out of it, then go do something else where you will get something out of it. And it might be that you just like drop down a level. So like, oh, this school is not satisfying one of my needs. I need money so I can pay rent and get food. So maybe I need to find something that will take care of that, and then I can come back to school. Does that make sense? I know it sounds like I'm trying to talk you out of going to school. That's only because I'm trying to talk you out of going to school. Because if all it takes is one Yahoo to say, hey, don't go to school, and you're like, oh, compelling argument there, Leach. If that's all it takes, so like, then maybe you ought to try it later when you have more motivation to do it. That makes sense? I realize that a lot of you are here under threat. Your parents have threatened you with like homelessness and destitution if you don't do this. I guess my point is I want you to see that as a threat. That's not cool. Don't threaten your friends. You know what I mean? I'm going to get angry calls from your parents. And then I'm not going to say anything. So I can't talk about this. You know what I mean? Like, even if you're like 12 years old, if your parents call me, I'd be like, oh, I'm sorry. If you want to know how little Johnny is doing in school, you're going to have to ask little Johnny. And then I really am an asshole because then I'm like, oh, come on, just tell me. It's like, oh, listen, if little Johnny is too afraid to talk to you, then I think you fucked up. Like, if your kids are afraid to talk to you and tell you what's going on, as a parent, you fucked up. You know what I mean? How's everybody okay? This is a Friday topic because I definitely don't want you actively thinking about this. I just wanted to put this idea out there that we're just adding dimensions onto things. By like taking our 0, dragging it through one dimension, giving us left and right, that's a length. Taking that length, that interval, dragging it into a second dimension with up and down, creating an area. Length times width. And then take that area and drag it through a third dimension to create volume. This is how we build things. Calculus is just length times width, but length is just variable. Instead of taking that one length and dragging it through the width, that one length is changing continuously. And we still want that area because it still tells us something. Anytime we can use multiplication, that's when we're going to want to find the area under a curve. Think about that when you go into the chapter, how do we measure speed? Because if this graph represents your speed or your velocity, then the area will represent how far you've gone in this width amount of time. We often just average things out. So I've got to drive 400 miles. If I can average 80 miles per hour, I can get there in, I can't remember what I said. I'm just going to go with 5. Thank you. 5 hours. I can't remember numbers for like longer than like 5 or 6 seconds. I should remember that it's always 400, always 80 miles an hour. I'm always speeding into the example, so it's always 5. But when you're averaging 80 miles per hour on that 5-hour drive, are you just starting off at 0 and immediately going 80 miles per hour? No. Sometimes if you're going to average 80, a lot of the time you're going to have to be well above that because a lot of the time you're going to have to be well below that. Like if I start in the parking lot here, I'm not going to be going 80 miles per hour until I get out on the 280, right? And there's like all that distance. There's like 5 minutes of going under 30. Well, maybe like 2 or 3 minutes of going under 30, then a few minutes going at 50, stopping, and then accelerating, and then stopping in front of Lenardi's, and then accelerating again. All that before I even get to 80. That's all dragging my average down. So after that, when I get on to 280, I'm going to have to be going 90 to counteract all that. Any question? Comment? I really should slow that example down. I think it would make more sense if we lived in like a smaller place and shit wasn't 400 miles away. But the United States is a big place. Your velocity, your speed is going to be continuously changing because you don't accelerate instantly. You're not like going 0 and then instantly going 60. It's going to take a good 6 or 7 seconds to get up to 60. That's a little bit aggressive. It's going to take a good 9 or 10 seconds to get up to 60. And some of you is like, well, I have a Tesla. It's going to take me 3 seconds. It's like, but you can't do that all the time, especially if you got to drive 400 fucking miles. You can't be like all putting it in plaid mode and just like gunning it, because you're just gonna use all your battery right away. Do you know what I mean? Any questions? Think about 0, drag to length, drag into an area, drag it into a volume. Multiplication is how we do that. Multiplication is addition when everything is constant. So what happens? When we want to multiply, but one of our factors is continuously variable. Don't think about that over the weekend. I want it sitting in your subconscious. This is called Inception. They made a whole movie with all this shit going on about it. It's like, oh, dude, just like say the thing around the person. And then that's how you do Inception. I don't know. There's no guarantee that it lands, but I've just done Inception on all of you. I should bring a top and spin it. All right. That's it for today. I will see you all. That's it for this week. I will see you all on Monday. Everybody have a good weekend, and thanks for playing.